Testing on YouTube. Testing on YouTube. Testing, testing, testing. Testing on YouTube. All right. Testing, testing, testing. I got a pop filter for you guys, so hopefully you don't have to listen to me breathe. Still working on this audio. It's a forever work in progress. How's it going, Tarun? All right. YouTube is working. The last one we have to confirm is X. So once X starts working. Let me spit out this gum. A little bit of that work juice from that gum. There's caffeine in it, that's the secret. All right. I think it should be live here on X in a second. Let's confirm. It's going to take like 30 seconds to start. X is a little slow. All right, I think it's live. It's live. Let's check. Go, go, go. Are we live? Let's check. I think we're live. All right, perfect. Looking good. We're live on all the platforms. So let's go ahead and get this started. How's it going, Ed? Good morning to you as well. Welcome everybody to another cozy, relaxing Hoopo stream. Today we're going to be diving into the world of agents. We've done some streams on agents before, but I think it's been a couple weeks since we looked at what's been going on. So we got a bunch of papers pulled up. How's it going, Timothy Stewart? Timothy provided a bunch of these papers, so props to him. And how's it going, Oma? All right, so I wanted to maybe start this stream with a little bit of controversy and drama that has been happening. So if you guys remember, there was this startup that released what they called Devin. And Devin was an agent, which is basically an LLM that has access to tools and kind of operates in a loop. And they were kind of advertising that it can basically go on Upwork and solve these different programming tasks. And there was people memeing, this is the end of software engineering, we're all doomed, and so on. But then just a day ago, people started posting on Hacker News here. Hacker News is kind of like a Reddit, but startup-themed Reddit, specifically kind of hosted by Y Combinator, which is a famous startup accelerator. And people realized that the demo that, this demo that Devin is showcased in is actually fake. So in the video demo, the problem it was asked to solve doesn't match the stated requirements of the customer. It's shown fixing errors, but the files it's shown editing don't actually exist in that repo. And some of the errors it's fixing are nonsensical. The video makes it look like Devin did the task quickly, but the timestamps show the task stretching over many hours and even into the next day. So not looking good. You know, basically this demo is faked. Devin does not work anywhere near as well as they're saying it works. And that's not a good thing for agents. So I come from the robotics world, so fake demos are pretty much par for the course there. Like any robot video you see, it's been very curated. The task has been picked. The cutting is done such that like you don't really get to see the negatives of it. Even like the Optimus demos or the Figure AI demos, like there's so much cheating that goes on in these robot demos. So I'm pretty used to it, but seeing demos in a pure software agent that are faked is a little bit sketch. And that's what we get from these papers. So we're going to be looking at a bunch of different agent papers, but the gist I'm getting from these papers is that the agents are just not quite there yet, which kind of makes this whole Devin situation make a lot more sense. So for example, here in this OSWorld benchmarking paper, they give you the raw numbers here. While humans can accomplish over 72% of the tasks, the best model achieves only 12% success, primarily struggling with GUI grounding, operational knowledge, and so on. So agents are getting oversold, and we're here to see where they are actually at and not where the startups that have a vested and existential interest in making you think that the agents are already here, they're going to kind of tell you that the agents are ready to rumble, but they're really not. How's it going, Khalil? How's it going, Tarun again? Okay, so Apple is working on GUI grounding Ferret UI. Yeah, pretty much everyone is working on agents. These are all academic groups. Some of these groups have backing from bigger companies. So for example, here, Cisco Research in the survey paper. This one here, you have Salesforce Research. This paper here, Wilbur, is from a Bardeen.Inc. Bardeen is another kind of Devin-like startup. It's basically just some startup that's like advertising some agent that can basically, I don't know, like do Google Sheets and emails and kind of things like that. So what else? We got this paper, Microsoft Research. So all of these agent papers, they're technically academic papers, as in like the authors are usually students and researchers at some academic institution, but a lot of these have companies kind of helping in some way. But we can safely assume that all the big companies have people working on this agent problem. Jan said that we can't achieve AGI with LLMs. Yeah, so Tarun is mentioning Jan LeCun there, who he's a godfather of AI, I guess people like to call him, but he's been working on AI for a very, very long time. And he's a little bit convinced that the current wave of AI based around these language models is not going to get to AGI. I think they're already at AGI. I'd actually disagree with LeCun on that. And I think that this agent stuff is very, very close. So even though it doesn't quite work as well as we want it to work, as was shown by kind of this Devin situation, I still think that these are very impressive and we're very, very close to an agent that can kind of do things. How's it going, Sarah? And how's it going, Jack Z? All right, so we're going to start with this paper here. This is a paper called A Survey on Large Language Model-Based Game Agents. This is a survey paper, so kind of a meta point here. There's different types of papers. Not all papers are the same. One general category of papers is called survey papers. In survey papers, the point of this paper is not to introduce any kind of new algorithm or some kind of experiment or something like that. Usually with these survey papers, what they're doing is they're cataloging other papers. So they're basically going through a huge chunk of papers. You can look at the reference sections for survey papers are absolutely insane. Look at this. You got like 6 pages of references, over 170 different papers. So these survey papers, they're just kind of summarizing a bunch of other papers. And they're quite useful. So if you actually want to learn about a new niche that you don't have a ton of experience with, survey papers are actually what you want to be targeting because they aggregate all the information for you and then present kind of the learnings in usually a pretty clear way that makes it very easy to get a not a very deep view of individual things, but a very broad view of a specific niche. So this paper gives us a broad view of agents, specifically agents that are being used for video games. And they actually have a very interesting table here where they basically go through all the different games. I think it's this one here. And specifically what type of game it is. So they kind of create like a category of games. So there's what's called adventure games, competition games, communication games, cooperation games, simulation games, and crafting and exploration games, which is kind of cool. I love this this kind of breakdown of games into different categories, and then seeing which ones are we really getting good performance in with these language model agents, and which ones are kind of the harder ones to do. I thought they had a table with these games. Is it this one? No, it must be further up. Okay, but they break down these game agents into their subcomponents, and the rough subcomponents, and we're going to see in all of these papers, they kind of like, all of these papers have some notion of a perception or an observation state. Memories, right? Some kind of retrieval augmented generation where you're kind of going into a memory bank, into some kind of cold storage, and retrieving things in order to improve your performance on that individual task that you're doing right there. Thinking, which is using multiple autoregressive steps that aren't necessarily outputting an answer, but are outputting more context, which you will use to then get to the final answer, right? So this kind of spending compute to just like reason in natural language, which is kind of what humans do in their own head, which is really cool and kind of creepy. But an LLM can do that too, right? It can kind of, you can spend compute to just sit there and output tokens, and those tokens will then be used to ultimately output the final token, which is going to be the answer for whatever game you're playing. Role-playing, which is really, role-playing in this paper, they're referring to this idea of giving LLMs a kind of like an identity, right? So in a lot of these papers, maybe they have multiple LLMs. They have an LLM that is the boss LLM, and an LLM that is the friendly LLM or something like that. And they give each of them a different system prompt, basically. And then that role or that kind of different system prompt results in different behavior. And then you can benefit from kind of multi-agent situations where you have different agents that are embodying different roles. Action and learning. Action is just kind of the action space. And then learning, of course, whether or not you're pushing gradients or you're just kind of building up this memory bank. A lot of different ways that you can construe learning. Okay, so in this paper, they use the multimodal LLMs. So if you've watched some of my streams before, I am in a holy war against this particular abbreviation of multimodal language models. I'm a huge fan of VLM for vision language models, right? GPT-4V to me is a VLM. But in the Apple paper, they called it a multimodal LLM, MLLM, which is kind of like the worst possible abbreviation. It's kind of like WWW, where it's literally harder to say WWW than it is to say World Wide Web in terms of like the amount of like syllables it is. And multimodal LLMs or MLLMs is also a mouthful. So I don't know who's pushing for this, but they need to stop because it's a terrible abbreviation. And they have an even worse abbreviation here, LLMAs, for LLM agents. I don't know. Terrible abbreviation. Stop trying to own the SEO around this, guys. Current LLMs rely on decoding and generalizing pre-existing knowledge derived from pre-training data, right? The reason these agents are so good is because language models have been pre-trained on so much data that they have an internal world model that is scarily good. AGI is capable of discovering and learning new knowledge through experimentation and experiences in the world. This is, in this paper, they don't want to say that current LLMs are AGI. They kind of want to say we're advancing towards AGI. I've made this rant before, but I think we're already there. I think the AGI, the key word there is the general, and the fact that language models are extremely general, right? They have medical knowledge, but they can also play Minecraft. That to me is like the definition of generality. So I think that LLMs are already AGI, but people have kind of moved the boundary a little bit further, and now to them and to a lot of people, such as even Sam Altman and Jan LeCun, AGI requires this agentic kind of self-improvement loop, right? So what they call discovering and learning new knowledge through experimentation and experience in the real world. Blah, blah, blah. Traditional RL, they kind of shit on that a little bit. RL has kind of disappeared a little bit, but now it's also coming back, and we're going to see in a couple of these papers how they use the reinforcement learning kind of paradigm in order to solve and think about some of these problems with agents. Okay. How's it going, Majetti? How's it going, Tarun again? Tarun, you keep posting, and I keep thinking that you're joining the chat for the first time, but you've been here since the beginning. All right, so in figure 1 here, this is the conceptual architecture of LLM GA. So they've reviewed whatever this is, like 100 different agent papers, and then they've basically said this is the rough system diagram for all of these. You have some perception, which is your state space in reinforcement learning terminology. It can be anything from images, text, state, which is kind of some structured information. That gets fed into the LLM, which is actually here. The LLM has some context. That context can be augmented and replaced with some amount of memory, right? You have reasoning, reflection. I think they have more specific definitions of those later on, but this is kind of like chain of thought, RAG, things like that. Role-playing, which I feel like, I don't know, to me, this part still seems a little fuzzy, like the abstractions they create here, we're going to see in these other papers, but there's a lot of kind of churn and different opinions on like the right way to have this loop right here. And then finally, the output of all of this is going to be your action space, which is going to be what you actually input into the game. All right. In the perception, why don't actually we move to this next paper, because I want to use this next paper to show how a lot of these ideas are being recycled from reinforcement learning. Jan mentions the Moravec paradox, where AI has mastered chess and the bar exam but can't clear a dinner table like a 10-year-old who can learn in one shot. Yeah, I understand his arguments, but I think they actually can. You know, I think that if you look at where robotics is right now, these language models are enabling clearing a dinner table like a 10-year-old, right? And I think if you froze the progress of language models and just we had GPT-4 for the rest of time, I think if you gave robotics 2 to 3 years to wrap GPT-4 and the vision language models inside these type of agent loops, I think GPT-4 would be able to clear the table like a 10-year-old. And then at that point, you can't hide from the fact that that's AGI, right? If it's running in a robot and it can talk to you in natural language with text-to-speech and speech-to-text, and it can answer questions about medical stuff, it can answer legal questions, it can play Minecraft, and it can clear the dinner table with an embodiment of a physical robot arm, I challenge people to say that that's not AGI. All right. In this paper here, OSWorld, this is a benchmark paper. So we saw how this is a survey paper where they basically survey a bunch of papers. This is a benchmark paper. A benchmark paper introduces a new benchmark or test that people can use to evaluate different agents. So basically in this paper, what they do is they introduce OSWorld, first of its kind, scalable real computer environment for multimodal agents. What it really is, it's a virtual machine. So basically an operating system such as Windows, Ubuntu, which is Linux, and Mac OS. Ubuntu is my favorite Linux distro, by the way. I know that some people don't like Ubuntu, but it's by far the best, and that's just my opinion. But this virtual machine here is basically creating a little virtual computer with a little virtual screen, with a little virtual mouse and a little virtual keyboard. And the agents can try to perform some task in that, right? They have some examples of what the tasks look like. Let's see here. Widely used web and desktop apps, OS file, input and output, multi-app workflows. I think they have more examples here. Yeah, Chrome for web browsing, VLC for media playback, Thunderbird for email management, VS Code for coding, LibreOffice, which is basically kind of Ubuntu's document and PowerPoint type stuff, handling spreadsheets, documents. So OSWorld is trying to create a benchmark that we will be able to use to benchmark all the different agents that people are going to create over time with over 369 computer tasks, and it's all inside these virtualized machines so that you can isolate the agent and see everything it does, right? Know exactly where it's moving the mouse and so on. And one interesting thing that they do for this, which I thought was kind of cool, is they use the accessibility features, which is pretty badass. So there's a whole like slew of tools which are called accessibility tools for assistive technology. So basically people who are blind or people who have some kind of disability, maybe they can't hear, maybe they can't use the mouse, maybe they can't use the keyboard, they can't see, right? Over the decades, people have come up with all these different tools that allow people to use the keyboard and mouse without, maybe they don't have hands or something like that. So it's like, or if they're blind, it describes what's on the screen. So I think that this is a very good set of tools to use to then give access to the agent, right? So basically the agent is controlling Ubuntu and Windows and Mac OS through the tools that are designed for humans that have disabilities, which I thought was a very clever solution. And the other nice thing about this paper is that it's entirely, the action space is freeform raw keyboard and mouse control, which is better than other action spaces. So the action space is this, right? It's the actual final thing that you use to control the game world, right? In a game, it might be a one-hot vector that describes like the 4 buttons that you could click, right? So then effectively what you're trying to do is solve the classification problem at this step. What action am I going to take? Well, my model's going to output some probability distribution over 4 possible states, and then whichever one is the most high likelihood button that I'm going to click, that's the one I'm going to click, right? And people have done that for these type of tasks as well, where they basically give it the buttons to click, but that's not really what we want, right? We want the agents to be able to literally use the computer like a human, which means moving the mouse. So you can see here, this dot represents the fact that we're not giving the agent like access to an API where it can close the window or open the window or click on cell number C2, right? It actually has to literally click on cell number C2 based on a mouse position. It has to literally click on icons and drag them. So this is a harder action space, but I think it's a better benchmark. And it's a good benchmark because the best model achieves only a 12% success, right? I think we saw in the previous agent papers that we read, they introduced a benchmark, but the benchmark was almost solved. Like GPT-4V was getting like 90% on the benchmark, and that's not what you want, right? You want to release a benchmark, and when you release it, all the state-of-the-art models are terrible on it, right? Because you need to have a lot of room for improvement in order for a benchmark paper to have any longevity, right? So you want people to continue to cite this paper. You want people to continue to use this benchmark in the future. You have to make it difficult enough that it's going to take a couple years until we start getting 99% success with all of them, right? Kind of like how ImageNet is almost solved at this point, and that makes it a bad benchmark. I think the fact that this one is very clearly not solved makes it a good benchmark. Okay, so They benchmark a bunch of different things here. GPT-4V, Gemini Pro, Claude 3 Opus, Mixtral, Cog Agent. One thing that they don't benchmark, which actually came out recently, I'm going on all kinds of tangents here, is Grok 1.5V. So this was kind of a stealth release. Literally didn't find out about this until this morning, but Grok, which is the X or Elon's AI company, just released their own vision model. It seems kind of on par, so they compare it here to GPT-4V, Claude Opus. It's better on kind of specific benchmarks, but worse on other benchmarks. So I don't know, it's kind of on par. So that's great, you know, because a world where you have multiple providers that are all giving you roughly the same model is better than a world where only one provider has the best model, right? If GPT-4V is about the same as Grok 1.5V and that's about the same as Claude 3 Opus, those are three different companies. They're going to basically try to beat each other on the price, right? So that type of competition will drive the price down and then make it better for you, the consumer and the user of these vision language models. So we don't really know where it is on this benchmark, but that's something that someone could do, right? You benchmark Grok on OSWorld. The sound is so much more smooth. I appreciate it, Sarah. I put a pop filter on this mic and I was messing with the filters just because I've been listening to some of my streams and the like breathing is like cringe inducing. So I'm trying to like fix the audio. So if any of you people actually know about like audio and you're like good at that, definitely give me some tips. I have like a filter, I have some settings here on OBS, but I'd love to make that better and better, you know? All right. What I really wanted to show in this paper, does inference speed not impact in these game agents? Yeah, so Tarun is asking a question where ultimately the game environment, right, especially for a game that is maybe a competition game, right? In a competition game, you're going to need to be very, very fast, right? Because the game moves quickly, right? So inference, which is how long is the process of actually autoregressively producing tokens with your language model, if that's very slow and you can only take actions at a very slow cadence, you're really not going to be able to play any kind of competitive game. So that's definitely true. There's a reason we don't see language models playing like first-person shooters, right? First-person shooters are probably the most reaction time, kind of like input speed sensitive games. You need to be like extremely fast, versus a communication type game, right, is usually turn-based and like diplomacy, and that's going to be way easier, right? Because you can just wait. You can spend 10 seconds of inference, especially if you're doing things like reflection and multiple chain of thoughts and RAG, where you have to go and find some information, then pull it up and run inference again. So that's why communication games and games that are turn-based, so you can spend a lot of time doing inference, you're going to have much better performance than something like a first-person shooter. I don't even know if I've seen a first-person shooter being solved with an agent. It'd be nowhere near fast enough. There was one with Doom, I believe. That's interesting. You're telling me that it was like real time, or were they freezing it? Because sometimes what they do with these type of things is they freeze it. The game is not real time, right? So they're running this game inside some virtualized environment, right? So they can decide when to step the environment, right? So they can spend 10 seconds doing inference and then step the environment by like 1 frame, and then spend 10 seconds doing inference and step the environment by 1 frame. So in that sense, you're kind of slowing down the environment to the speed of the agent. But playing Doom in real time, I don't know how fast you need to be for that. All right, finally I'm getting to what I wanted to show you guys. Okay, so in the OSWorld paper, they actually start here in the task definition. So task definition is the section after their introduction where they kind of describe it. And they basically steal, or not steal, but this is reinforcement learning, right? So for example here, Our agent task can be formalized as a partially observable Markov decision process with some state space S, observation space O, action space A, transition function T, reward function R, current observation OT, executable action AT, new state ST plus 1, and then some execution-based reward function R, right? So if you guys are familiar with reinforcement learning, this is reinforcement learning, right? So for those of you that are not super familiar with it, I have here the Wikipedia page for a Markov decision process. A Markov decision process is effectively the inductive bias or the model for reinforcement learning, right? Anytime you're using reinforcement learning, you're starting with some set of assumptions, and usually, pretty much for all of them, that assumption is this Markov assumption, right? Which is basically saying that your world is a set of states, right? So in chess, this might be the current layout of the board, right? The position of all the little pieces on the board. And you have a transition function that says, okay, well, if I take a certain action, maybe I move my horse from this point in the board to this point of the board, that's going to transition you from one state to the next state, right? And the reason this is a required assumption to even do reinforcement learning is because in reinforcement learning, what you're really learning to do is take the appropriate action in the appropriate state, right? And that only works if the states are the same every time, right? So in chess, this is perfectly fine, right? If you have a specific board position, right, and you take an action in that board position, 1 million years later, if you find yourself in the same board position, that action is also going to be good, right? So like the board position is like the states are discrete and they're the same no matter what path you took to get there, right? So that's why chess is very, very good for reinforcement learning, because it's a very, very, like, it adheres very strictly to this Markov decision process. Now, that's Markov decision process. The partially observable here, which is what makes this a POM-DP, a partially observable Markov decision process, is just a simple little extra piece here, which says that the state S is known. Otherwise, if the state is not true, which is you don't know it, then it's called a partially observable Markov decision process, which is basically just a fancy way of saying that in a Markov decision process, the state, you know exactly what the state is. In a partially observable Markov decision process, you don't actually know what this state is. You have some observation of it that only partially kind of tells you whether or not you're in that state or not. So in robotics, it might mean that you have some joint angles, but you don't actually know the true joint angles, right? Maybe you just have some observation of your joint angles, which are fuzzy and potentially maybe even wrong, so they're just partially observable, right? That's what that comes from there. But I actually think that I'm taking a little tangent here to talk about what I don't like about the Markov decision process is that this is not how reality works, right? The Markov decision process is kind of a very materialistic view of reality where you have states that are all the same and there is some ground truth state, and then you have actions which take you to the next ground truth state, and there's actually like a real state. But not to get too metaphysical with you guys, but the Nobel Prize was recently given to some people who proved that the universe is not locally real, right? And what this means is that this assumption that there's some kind of base reality, and that base reality has some state, and that you're existing in this state which is true, aka ground truth, that's not actually true, right? If you actually look at the way our world works, it's more fuzzy than that, right? Everything is kind of existing in this quantum cloud of possible states, right? It could be blue or it could be red, right? That's kind of what the pictures here are supposed to say, is that there's an apple, but it could be a green apple or it could be a red apple, right? And it's kind of existing in a superposition of those two possible things, right? And the whole universe is not locally real basically means that everything is like this, right? Where there actually isn't a table here. There may be a table here, but maybe there isn't a table here, right? And that makes absolutely no sense with a Markov decision process, because the Markov decision process is very clear in saying that no, there is a state of the board, there is a current board state for this chess game, and that is true, right? It's not like it might be partially wrong or that pawn might not actually be there. It's like no, it actually does exist. There is a state. You are taking an action which leads you to another state. But I don't know. Quantum stuff is not really relevant at our scale. This Markov stuff is more about getting things tractable and computable. Yeah, that is the truth, right? Like I said, Markov decision process works, right? It's an assumption, but it works, and it works because we have things like the chess AIs that work quite well. But the more you move away from chess and these type of games that are very discrete and have very specific states that you can return to, and the same state is the same state every time, the less this assumption holds. So going from chess to something like the Dota video games, right? You're starting to lose a little bit of this MDP. It starts to become not as good of an inductive bias. And then once you go into robotics in the real world, that's when I feel like weirdness kind of associated with this starts to feed in, right? Because in the real world, like the light that is reflecting off things, it's like you're never really in a state that is repeatable. Every state is different, and even then, the state that you think you're in is not really the state that you are in, because you're just observing it through light, and the light is scattering off things that may or may not be there. I don't know. I'm getting a little bit too ontological here, but I do feel like there's some issue with the Markov decision process. All right, but bullshit aside, the interesting thing is that we've recycled reinforcement learning for language model-based agents, right? When people think of reinforcement learning, they're usually thinking of deep reinforcement learning. And in deep reinforcement learning, right, you're using a deep neural network, which is a function approximator, to approximate these transition functions and these reward functions, right? And the input or the state space for deep reinforcement learning might be a vector that represents the joint angles for a robot, right? And the action space might be a one-hot vector that represents the 4 possible buttons that you're clicking on your game, right? So in that case, these neural networks that define the transition function and reward function, they're inputting and outputting in these state spaces and action spaces that are vectors. But in these agent papers, and this paper does it, and then also this paper does it. So this is a Wilbur adaptive in-context learning for robust and accurate web agents. They also basically use the partially observable Markov decision process. But the interesting thing that everybody is doing now, which I think is pretty cool, is that the action space is text. The state space is text. The observation space is text. So basically, rather than the observation O of t being like, here's the state of the board for a game of chess, and it's like a discrete state, the state is now a natural language instruction. So basically, we're still using neural networks, right? We're still using a transformer, which is a type of deep neural network, but the transition functions and the reward functions are almost now becoming sequence to sequence, just natural language to natural language. So it's like we're taking all the stuff that we've done with reinforcement learning and now saying, okay, if you replace these deep neural networks with a language model, now you can just make the input and the output to that transformer natural language. So now everything is being done in natural language, which I think is a lot closer to what humans are doing, and I think it's a lot more natural, and it's actually, I don't know, I keep wanting to say cool, but it's like, I think that's kind of very interesting to me, where basically now, for example here, right, this is the output. This is the action space. The action space is not like some regression target that's like telling you the velocity of your mouse cursor. It's literally like text. The output is text. The input is text, right? So it adds a layer of fuzziness that I think balances out the inductive bias that is the Markov decision process, right? Because the text is more fuzzy. So if your state space is just natural language, the description of the state is going to be a little bit more fuzzy. You might have multiple different paragraphs of text that kind of like all mean the same state, and in that way you're kind of allowing a little bit more of that fuzziness in there. And I feel like it's a good way of taking RL, which I think was a little bit old, a little bit dated, a little bit worn out, and rejuvenating it for the modern kind of language-based model era. Infinite action space. Yeah, that's another nice way of putting it. RNNs learned through Markov frameworks actually do have memory due to architecture specifics. Yeah, and like a computer is very much adheres to the Markov decision process, right? A computer has discrete, actual, locally real states, right? So a computer is locally real. It's like if you make every single input to your program the same, the program is going to deterministically output the same thing, right? So like computers, because they're based on this binary system and there's like a little transistor there that actually has, it's either 1 or it's 0, right? Computers do follow it, but I just think the real world is not like that. And using natural language as the state spaces, as the action spaces, as the observation space, I think that's a good way of kind of making it all work. Any variable that has time-changing impact on state space cannot be measured long enough. Yep. Okay. I think there's a couple more things in this paper. The virtual machine. I thought that was kind of cool. The one thing I don't like is that the VM that they use is you have to pay for it. That was really fucking like annoying and not that great. I think it might be this one. They have a link to it. I'm trying to find it. This. Let me see if I find it. Okay, I don't find it. But you actually have to pay for this VM, right? So it's not like Docker that's free, right? Which is kind of annoying. I feel like if you make a benchmark and you want people to use your benchmark, you can't rely on some software package that you pay for, right? Like nobody's gonna use your benchmark if they have to buy some license for your VM emulation software. VirtualBox. Yeah, there you go. VirtualBox. Oracle VM VirtualBox. Maybe it's free? The only professional solution that is freely available? Huh. Okay, maybe I was wrong. I just clicked on one of the links that they had here and it took me to this thing where I had to pay for it and I was just like, dude, fuck that. But it seems like maybe I was wrong and you can actually use this. Okay. Thank you for that, Timothy. Mouse sounds like I'm moving my hands in a bag full of rice grains. I'm sorry. I'll try not to scroll. I'll try to click like this. Okay. Let's move to this one here. So this is the Wilbur. This is Bardeen, which is the startup that's basically doing this. And this is a preprint. So actually, we're going through all the different types of papers, right? So you have your survey paper, you have your benchmark paper, and then this is a preprint paper. A preprint basically means that they put it on archive, but it's not even officially accepted into a conference yet or like a journal, right? That's what the under review means, because you have to go through the review process to get accepted into these journals. But this world is moving so fast, the world of ML and AI, that like a bunch of these papers are actually preprint, under review. So that's how fresh the research that we review in these streams is that it's not even been officially reviewed, right? We're really at the bleeding edge here. Wilbur, an approach that uses a differentiable ranking model and a novel instruction synthesis technique to optimally populate black box language models prompt with task demonstrations from previous runs. So optimally populate the model's prompt. So this is effectively a RAG, right? Retrieval augmented generation, which is trying to figure out what to put in the prompt of your language model such that it effectively completes the task. So if we go back to our survey paper, what they're basically doing is they're trying to figure out how to choose the right things here in the memory to put into this context such that the action that gets outputted is more accurate. So they claim state-of-the-art results on Web Voyager, but hard to say, because Web Voyager is just one of many different benchmarks. We have OSWorld, and then we actually have another benchmark paper here. This one, Web Arena. So this is another benchmark paper where they create a Web Arena environment. And this one also, look at this, our best GPT-4 agent only achieves end-to-end success rate of 14%, significantly lower than the human performance of 78%. So both of the benchmark papers are basically telling you that the the performance of current LLM agents it's like terrible, 12%, 14%. So we still got some ways to go. Back to this one. Paper says VMware. Okay, that's what I remember looking up. VMware. Yeah, there we go. This is what I remember reading. So I clicked on something, I ended up here, and I was like, VM Workstation Pro? Like products? Like you have to buy this? Like this sounds gross. But I don't know. It sounds like there's free versions, so hopefully I never have to sign up for this crap. Intelligent agents interact with the web through a browser. The success rate of the best web agents is a far cry from that of experienced people familiar with the websites. There are more than 1 billion websites in the world. All right, here's the Wilbur agent. Little diagram. It utilizes retrieval, synthesis, action, and verification. So you're seeing, again, a lot of these same exact concepts, which are really just the recycled concepts from reinforcement learning with slightly different names, right? So retrieval, you have your knowledge bank. This is your memory. Your knowledge retriever pulls information, which is just text, right? Everything here is natural language. It's pulling specific pieces of text from that. That gets added to the context here. You have different models here. Demonstration ranker. The demonstration ranker here is a model. The demonstration ranking model is trained to predict whether the action will lead to a successful execution or not and optimally populates a model's context. So you have a transformer, which is consuming text and then outputs basically a reward that is saying this is good or this is bad, right? And that is also a recycled concept from reinforcement learning. And one version of that is called a reward function, which is a mapping from states and actions. So given this state and this action, what is the reward? The reward is going to be something like 0 or 1. Usually that's kind of the standard, where basically 1 or a positive number under 1 if it's a good state, or 0. And another little tangent for you guys here is that if you remember OpenAI's kind of Q star, and everybody's like, whoa, what is this Q star? If you know about reinforcement learning, that's, you know what that Q is. So Q is basically the same as that reward. It's not quite the same, but you can think of it at a high level. That's really what it's doing, right? Actor critic is a type of framework or a niche of reinforcement learning where you have an actor, which is the model that's actually choosing what action to take. And then you have a critic that is kind of determining how useful a given action in a given state is, right? So it's kind of giving you a score, right? So here you see this Q function here is consuming the state S and the action A, right? And I like the way that they summarize it here. The critic estimates the value function. This could be the action value or the Q value or the state value. So these are other types of critics, right? And if you think about what is OpenAI's Q star, it's basically using a language model as the Q function, right? So OpenAI's Q-star is effectively this. It's a language model that is consuming natural language and then saying, okay, is this a good thought or a bad thought, right? In this case, the Q function, or the demonstration ranking model, or whatever they want to call it here, what it's ultimately determining is, okay, here's text from my knowledge bank. Is that text worth putting into the context? That's one way to do it. Maybe what OpenAI is doing, because the star at the end of Q star is probably coming from A star. A star is an algorithm that kind of moves through the a graph in a optimal way. But what the Q star is doing is it's probably just evaluating state action pairs, right? So imagine a language model that sits there and consumes a state and an action. So it's consuming, okay, this is the state I'm in. This is the action I could take. This is the action I could take, or this is the action I could take. Run each of those through the Q model, and the Q model will basically give me a score, and then I can use that to determine where to go there. And you can imagine doing this for like chain of thought, right? So maybe you have a language model, you're trying to figure out what to put into the prompt or the chain of thought, and in order to figure out what to put in that prompt or what chain of thought to go down, you basically use this Q model to evaluate that. And the magic is that all of this is in natural language space, right? So your Q model is in natural language space. It's consuming the state space is natural language. The action space is also natural language. So you can just use a transformer there. Maybe you want the output of this to be a number, but I don't know. That's probably what Q star is. It's probably exactly this. That's why Hoopo has strong forearms. I don't know if my forearms are particularly strong, but Hoopo, how do you see Q star differently from reward modeling in ChatGPT? So Q star, the star there is what makes it different, right? The star refers to A star, this right here, not Asterion, A star. A star is a path planning algorithm. A star path planning. See if we can find a nice little GIF for you guys. There we go, here. Is this A star? A star search algorithm, Wikipedia. Boom, there you go. It's basically just a way of traversing a graph. See, like here you go. You're trying out this state, you try out this state. It's like somewhere in between a depth first search and a breadth first search, if you want to think of it that way, right? And Q star is basically making some Q function that consumes states and actions, which are all natural language, and then using that to search over the possible like forward state space and action space of natural language to determine what stuff to do. So that's what makes Q star different from reward modeling. But at a high level, really, it's kind of the same thing, right? Okay, what else is there in this Wilbur paper? I thought this was kind of cool. Autocurriculum, which generates plausible goals to populate demonstration banks. So the demonstration bank is a database that contains demonstrations or trajectories or sequences of state actions, right? So basically you have some sequence that says, okay, here's the state at time, the state and the action, the state and the action, the state and the action, the state and the action. Every single one of those states and actions ultimately leads to this goal of like opening some Chrome tab and then clicking on something, right? And you could try to get a bunch of expert humans to do that, right? So get a bunch of humans to sit there and click on things and complete tasks inside these benchmarks, virtual environments, or you could figure out how to generate these kind of more in an automatic way. So you're kind of trying to figure out how to get good state action tuples and trajectories of those sequences of state action tuples that you want to eventually learn from. And in order to do that, they're going to do this auto curriculum, which is basically generating some goal and then trying to reach that. And you can see this in robotics too, right? Where it's like, okay, we need to have a bunch of examples of like goal conditioned behavior. Let's just create a bunch of random goals and then try to reach it. So like, oh, try to make the arm move over there, and it's just like some random arbitrary position, and then try to make the arm move over here, and it's just some random arbitrary position, and you can eventually create this giant data set of trajectories, both successful and unsuccessful. Right, you're going to have some automated criterion that allows you to determine whether it's successful and unsuccessful. In this case, it's quite easy because it's a web agent, right? So you can say, okay, well, I have the state space of the actual website. Was this task actually completed or not? Right, and because you can do that, you can classify automatically whether the trajectory resulted in a successful or an unsuccessful thing. And then now you have the reward label, right? So you know successful means your reward is going to be 1, unsuccessful means your reward is going to be 0. And now you have trajectories with a reward label, so you can train a reward model, or what they're calling a demonstration ranking model, that tells you how good that particular sequence or trajectory was. And then eventually, you do that enough times, this demonstration ranking model gets good enough that now you can use it for planning at like inference time. And that's basically what this paper is. And a lot of these other agent papers try to do similar things as well. There's this other paper, this one here, Autonomous Evaluation and Refinement of Digital Agents. You got Sergey Levin on here. This guy's a legend in the robotics world. But this is kind of the same idea, right? Where it's like, hey, we want this idea of like an evaluation model, a model that kind of like the Q here, right? It's like telling you how good specific state action pairs are, or in this case, a little bit more like the whole trajectory of like, was that actually a good trajectory? Was that a bad trajectory? And then once I have enough of those examples of good and bad trajectories, then I can train this evaluation model or this reward model or whatever you want to call it. And then I can use that kind of like the critic in an actor-critic framework to train a policy, which is actually going to be the one that's actually performing the actions. Star usually refers to optimal in RL. Yeah, you could do that. That kind of goes to what Timothy Stewart is saying, that the terminology is a mess, right? There's a lot of words that kind of all mean the same thing. There's like 17 different ways of saying different things. There's all the like baggage of the original kind of formulation of reinforcement learning. Then you have now people coming in with their own kind of terms that they're using for this, right? Such as a knowledge bank memory here, but other people just call this memory, and so on. So it's kind of a little bit of a word soup, and everything kind of is a little bit fuzzy. But what I really want you guys to center on is that ultimately all these ideas, even though people are using different terminologies for them, it's all kind of the same ideas, right? Where you basically have this thing that tells you how good this reward function, this Q function, like this value function, this evaluation model, this, what do they call it here? Verifier model, like something that is basically looking at where you are at and what actions you're taking and telling you whether that's a good thing or a bad thing. And then something that is, transition function here is more predicting the next state. And this is more because it's a partially observable Markov decision process. But the transition function is like, okay, I'm at this state, I take this action, where do I end up? And you can also model that function with a deep neural network, right? Okay, question from Christopher H. Do you think that it is limited at expressing states because it kind of discrete and tokens are fixed? Yeah, so Christopher is making a good point that even though I was kind of talking about how natural language is much more fuzzy, and that's a good thing, technically it's still discrete, right? Technically, natural language is still limited to a set of specific letters, of which there's only a certain amount of letters and numbers. In practice, this is really just tokens. So there's a limited vocabulary of tokens. So technically, the state space for a language model is also discrete because it's like it has to be a sequence of these valid tokens. And those are innumerable, kind of like the possible states of a chess game board. But I think that the the state space of a sentence is more fuzzy. I don't know, like I feel like it's a bad way of describing it, but it seems to me like the representational capacity of like a sequence of tokens is a much broader kind of and more fuzzy state space, which more accurately reflects the reality as opposed to more kind of discrete and explicit state and action spaces like the one I keep talking about, which is like a one hot like controller, right? Where it's like basically your action space is just which of these 4 buttons are you clicking, as opposed to your action space being all possible sequences of tokens of which there is some limited vocabulary of them. How's it going, Emily? No problem. We're kind of just riffing here. There's a lot of these papers. They all kind of have the same idea, so I'm kind of just mostly just ranting while I kind of vaguely scroll through these papers. Okay. We're talking about the scalable knowledge bank, website conditioned demonstration. So website conditioned demonstration is just a fancy way of saying that all of these models, whether it's the action, the model that's ultimately producing the action, which is this policy pi naught here, right? It's conditioned on this SFT, this state, and the state, you can just literally have the website be part of it, right? So in this case, since everything is in natural language, you can say, okay, well, here is my demonstration of click on this and this and this and this, but every single one of the states in that trajectory also says, this is a Firefox web browser, and I moved over here, right? So like you can add the name of the website to the state, which is natural language, so it's very easy to add and remove things from that state, and such that your demonstrations are technically website conditioned. I thought this was kind of interesting. Backtracking and loop detection improves by 6%, and adaptive in-context learning and auto-curriculum leads to an additional 12% improvement. So backtracking and loop detection is a specific kind of thing here that they do where, because they have the full state, the kind of path that you took to get to the current state that you are, they can look and use this verifier LLM to see if you're looping, right? So these language models, one particularly heinous type of like mode collapse that they, or error mode that they can get into is that once you kind of repeat something in a language model, it wants to repeat it again, right? So language models really, really want to repeat the same thing that they kind of do that, right? And you've probably seen this where like your language model will get stuck on a word and then it'll repeat that word. And then once you've repeated a word twice, the most likely next word is also a repetition of the previous one. And then once you've repeated the same word 4 times, then the most likely token is just the same word again. So like they can get stuck in these kind of loops. So loop detection, which I thought was kind of a good idea there. And then what they call here adaptive in-context learning. In-context learning is a fancy way of saying that the language model is learning what to do, or it knows what to do because you've provided examples in context, which basically means inside the sequence of text that is being inputted into the language model. The learning is not, I think it's a little bit of a misterminology because you're not actually pushing any gradients there, right? It's not like you're pushing a gradient into the language model. The language model is the same language model. It's just that it has some examples in the context, and people call that in-context learning. And then in this case, it's adaptive in-context learning because the stuff that you're putting in the context is adaptive and it's based on what you're retrieving from your knowledge bank and then putting into that context. So it's adaptive in-context learning is just another way of saying retrieval augmented generation. It's all the same stuff, guys. There really is only like 4 ideas in here, and then there's just like a billion different ways of saying those same 4 ideas. Did I check the paper Grandmaster level chess without search? Off the top of my head, no, but maybe. I don't know. I read a lot of papers and my memory's pretty bad, so I kind of forget things really easily. Okay, so apparently some kind of interesting chess. They modeled chess state without giving it explicitly directly from moves. So is it basically chess, but they don't actually put the entire state of the board game? They like describe the state or something like that? I don't know. I don't know what chess data looks like, right? The LLMs have to have been trained on chess data because I bet you there's websites of chess moves, right? Chess game website. I mean, I'm not going to find it live, but like I bet you there's like a website that GPT scraped that's basically just like every single chess game ever played. And I think that there's actually some specific notation for that as well. I'm kind of speaking outside of my expertise here. I don't actually know very much about chess, but like there's like a specific like almost like a programming language that you can use to write down the states of a chess game, right? So like I imagine that GPT has seen enough of those in its pre-training that it has a pretty good kind of like world model for chess and like what moves are good and what moves are bad. Okay. Contributions. Learning in context from previous executions of the agent, which is just RAG. Task demonstrations using a novel trained model. Right, this is the actor critic. Once you have a good critic, you can train a good actor, and then once you have a good actor, you can explore more of the state space and thus get more information for the critic. So it's kind of like they help each other out, you know? Kind of like the generator and the discriminator in a GAN, although that's a completely different beast because those are usually much more explicit and much more tied together, but it's the same idea, right? Where you have something that's generating and then something that's critiquing, something that's acting, something that's determining the value of that specific action, and then using those to help each other. LLM scoring. Here's the reinforcement learning. The self-evaluation module, RHAT, which is effectively just the reward model. Demonstration retriever queries a demonstration bank and finds relevant ones. Individual actions also. Obtains both positive and negative demonstrations. So that's kind of interesting. In context learning, or when you're doing retrieval augmented generation, you don't just want successful demonstrations, you maybe also want unsuccessful demonstrations, right? So in the context of like a web agent, it might be like, here's a bunch of good things you want to do, and then here's things you want to avoid. Like, don't click on the X, don't click on this, don't click on the ad, you know? So that's kind of interesting too, how in context learning is not, you're benefiting from putting unsuccessful demonstrations in there, which is kind of cool, right? Because in a more classic reinforcement learning context, I guess there is the notion of like low value state action tuple. So like that's kind of like what an unsuccessful demonstration is, but knowledge synthesizer actor predicts an action A given the DT, DA, and L. So this is just, that's the other nice thing about everything in natural language is that you can just very easily compose these things. Executor performs the action, results in a new observable state. The reflection module compares your current observation and the new observation before determining whether to backtrack, continue, or finish. Right, so this is more of a like explicit one-hot action space. Right, so the reflection module really, it only has the choice of 3 things. So I bet you the final thing there is just a little vector of dimension 3. And then answer module produces textual response. And here's the loop. And these agent loops, like, this is really the more interesting part, right? Because this is the secret sauce, right? Like a company like Bardeen, the startup that is making this, they're not making the language model. So what are they doing? Their product is this. It's this agent loop and trying to figure out ways of making this as good as possible, right? And this is a whole new area of research right here. This is a paper called ResearchAgent, Iterative Research Idea Generation over Scientific Literature with Large Language Models. This is the same thing, right? It's the same thing we've been seeing in all these papers. It's just an agent with language models in the middle, kind of following a loop that is heavily influenced by reinforcement learning ideas, right? You have this notion of action spaces, observation spaces, reward models. But in this case, the loop, the agent loop, is specifically centered around this idea of research writing and researching papers. So in this case, the research idea generates problems, methods, and experiments designs while iteratively refining them based on scientific literature. You have an entity-centric knowledge store, which is effectively just another type of knowledge database, right? In this case, they're calling it a knowledge demonstration bank, and then here it's an entity-centric knowledge store, right? It's all just different types of the same kind of idea of like a cold memory storage that you can pull things into your context. But the one thing that kind of I'm noticing here is that all of these agent loops are task specific. So it seems like what we're doing and the way that we're solving and getting to language model agents is that we're using all these kind of assumptions and inductive biases that are specific to the task and using those to design an agent loop that is good at specific things. So in this paper, Wilbur is ultimately just an agent loop, but an agent loop that is all about clicking through websites, right? So there's different things inside this agent loop that are basically like specific to clicking through websites. Versus in this paper, you also have an agent loop that's using the same language models, but now the agent loop is kind of hard-coded for this problem of researching. And it feels to me like eventually we want to move to a world where the agent loop is agnostic, it's generic, right? If we want AGI in the sense that this paper says it, right, where AGI is discovering and learning new knowledge through experimentation and experience, kind of an agentic type of AGI, I think that we're going to have to figure out some agent loop that is identical for all tasks, right? Some agent loop that is general enough for every type of task. Because right now, what I'm seeing in all these different papers are task-specific agent loops that are narrow, right? And that's kind of where deep learning was like 5-6 years ago. 5-6 years ago, you had narrow deep learning models, right? You had a deep learning model that was specifically for medical stuff. You had a deep learning model that was specifically for poetry or something like that, right? And it was narrow in that one domain. And then we like kind of leveled up by creating these language models that are general, right? They can generalize to all types of sequence-to-sequence tasks. And it seems like we're kind of in the same place that we were at 6 years ago, but now with agents, where we have these very specific task-specific narrow agents, but someone needs to figure out how to make a general agent or a foundation agent that would work for all of these different things. Did they train the critic part, or is it still the same LLM? So I think in this one, in some of these they do. In some of these, for example, like the self-evaluation module, so like the self-evaluation model or this reward model right here, this reward function, which they're using a language model for. In those cases, yeah, they are training those. They are taking a pre-trained language model and then fine-tuning it on data so that it outputs a reward from 0 to 1 given some text input. But in some of these other modules, especially the ones that are more text to text, they're not actually touching them, right? So the actor LLM here, I don't think they actually push any gradients into this. This is just a frozen language model, and largely the way that you're changing the behavior is through putting some things in the context or not putting some things in the context, right? that whole idea of in-context learning, where you don't actually need to push any gradients. If you just change what's in the context, that's going to change the behavior. And again, I don't really like this. I don't like calling that learning, because to me, learning means that you're pushing a gradient, but we might have to reconsider what that means, right? Because think about nowadays we have longer and longer context, right? You have the Gemini 1.5 with 1 million tokens of context, right? At some point, I actually think fine-tuning might go away, right? If the context gets long enough that we can just fit our entire like data set or fine-tuning data set into the context, and that's good enough to get the behavior that we want out of this foundational language model, then we don't need to push gradients and fine-tune that foundational language model. And that also drastically simplifies the entire pipeline, right? Because right now, you can't even fine-tune some of these language models because the GPUs that you have available can't fit them, and fine-tuning is kind of complicated, right? You have to know how to program. You have to know kind of just how to do deep learning and machine learning in general. You have to curate these data sets. Think about how much easier it's going to be if every single language model has like a 10 million token context, and you can just take whatever fine-tuning data set you were going to fine-tune your model on and instead just copy-paste it into the context. And that in-context learning is basically parity with fine-tuning. So that might actually be where we end up. I know that that's maybe a controversial statement, but I could see that. I could see a world where we have these agent loops, and every single LLM in that agent loop is basically just raw. It's not fine-tuned on any specific thing. It's just you're changing and swapping what's in the context, or effectively prompt engineering your way to specific behaviors that you want. Doesn't that have a huge token consumption issue, which is inefficient and costly? Kind of, but isn't fine-tuning inefficient and costly? You know? Because when you fine-tune a model, one, not only do you have to fine-tune it, which you're going to have to do in the cloud and pay some cost for that, but then that model is gonna slowly over time get worse, right? Like if you fine-tune a specific version of Mistral, and then Mistral releases a new base model, now you got to fine-tune that new base model, right? So it might be easier if the foundation model is always the same. You don't have to have like some database that is storing all these different foundation models and pulling them up and occasionally retraining, fine-tuning models because the base model has been updated. Like you don't have to do any of that. You're just kind of putting in the text when you need it, and that's it. Why would you need 10 million tokens here? You don't. I'm more just trying to make an example. The Gemini is only 1 million tokens, right? So 10 million tokens is more what we could get to, maybe 2025, 2026. But what I'm trying to get my point across is that a lot of times when we think about engineering and research, we're constrained by the fact that the human mind doesn't really think of things in 10x, right? Where we're like, okay, well, this is what we currently have and blah, blah, blah. And here's all these different engineering tricks that we can use to make what we currently have work. But the better way to think about where the world is going, and the better way to think about the future, and this is how a lot of other researchers think about it too, right? Like if you remember that Ilya Sutskever interview, he was talking about like people don't realize that GPUs are going to get 10x, 100x, 1000x faster over the next 10 years, right? So take that same idea of like, okay, well, where are we at now? What if I 10x the context? What does that change? What if I 10x the size of these, right? So think in that 10x kind of mode where like, don't be constrained by the current situation, like be able to play in your head with 10xing things, and does that change it, right? So in my mind, I'm basically saying if you had 1 billion tokens of context, can't you just fit your entire fine-tuning data set into that context? And at that point, if you can fit your entire fine-tuning data set into the context, do you even need to fine-tune anymore, right? So that's kind of more what I'm trying to say. I'm trying to like extrapolate and say, okay, if we got 10x the amount of context, do we even need to fine-tune anymore? Okay. Most of this paper is kind of about what we've seen. It's kind of the same stuff, retrieving the top K relevant entity. So it's the same idea of the RAG, right? You're retrieving specific things from some cold memory and then feeding that into the context and then improving. One cool thing that they did in this paper is they actually used human evaluators. So evaluations with human judges, graduate school students from the United States and South Korea getting paid $22 an hour. I don't know if that's a high price or a low price, but that's a really good evaluation. I'm a big fan of human evaluation studies. And here in this figure, they compare, I mean, the relevance, clarity, average. So this is like reviewing research papers, right, and generating research ideas. But naive research agent, which is the red, versus research agent without entity retrieval, versus research agent, which has this entity retrieval, this aka RAG. And you can see how the entity retrieval adds a lot, right? So being able to go into this memory module and pull out specific things and then put that in your context and do in-context learning in order to improve your output, that works. That's basically what these charts are showing you, is that RAG works. And if we have bigger and bigger context, it makes sense that RAG, which is effectively benefiting from in-context learning, then it's going to be even more important. So Wilbur is just a well-thought prompt chaining. Everything is prompt engineering. Basically, every single paper that we've looked at here is just prompt engineering. You would still need to inject some kind of tuning data. It wouldn't go away. You would just do the tuning process as we know it today. Yeah, so beyond that, you're bringing up a good point, right? Where if we do everything in context, right? So if we really, really double down on this idea of in-context learning as opposed to fine-tuning, then the dataset curation part of fine-tuning, which is a big part of it, is going to have to be done live, right? So right now, if you want to fine-tune a language model on something, you need to create the fine-tuning dataset. And that fine-tuning dataset, the quality for that needs to be very, very high, right? So you basically need to curate that dataset, go through it, clean different things, put it in a specific format. You're going to have to do that for in-context learning as well, right? So, and that's really what these papers are. They're just kind of doing that dataset curation part of the fine-tuning, but now as part of this RAG framework. So how can we intelligently pick the dataset, quote unquote, that we're going to put and do in-context learning on, but really what you're doing is just putting it in the context and then the language model is just outputting based on that. In-context learning will make the inference a nightmare. Yeah, that somebody else mentioned that too, where you're going to have to pay the inference cost because now you have like 10,000 tokens of like crap every single time. But I think that I actually think that it's not as bad as fine-tuning. So there's a lot of like details there that kind of make or break it, but IMO, in-context learning, and fine-tuning are both bad. But I feel like in-context learning, especially if you 10x the context length, it's probably going to be more popular just because it's more simple. Okay, this is the Sergey Levin paper. I thought this one had an interesting little piece here where they basically talk about this dichotomy of, are you using a vision language model to caption the image and then using an LLM to do the reasoning? Or are you using the VLM to do the reasoning itself? And I've actually done both of these. So I think in this other paper, they also talk about it. No, I think it's in this one. Yeah. So in this paper, this is the summary paper, when they're talking about the perception, or aka the state space, one way to do it is to use these vision language models to basically take your image if that's part of your state space, and turn it into text, and then use a different model to do the text to text, right? So the language model is the one that's doing all the reasoning, but the vision language model also is a language model, right? It's just a language model that's been fine-tuned to output captions. But now you have two different language models here that makes your whole pipeline slow. And I actually think that this end-to-end here, where you're just using the VLM as the entire thing, this is kind of where we're going, right? Where if we make a VLM that isn't fine-tuned to just caption things, and it's tuned to answer questions and kind of have a little bit more reasoning still there. And I think the reason that they're not quite there is because a lot of times in vision language models, the language model part of that is usually some small little model, right? Like a 7B model. But we're seeing that in these more modern vision language models, they're using bigger and stronger language models, and then they're using multiple vision encoders. So once you do that, maybe you don't need this two-part process here where your VLM is just acting as a captioning model, and then the LLM is the one that's doing all the actual reasoning. So I don't know. And then if you combine that with kind of what we were talking about around the idea of big context length, right? So if we're getting better and better at in-context learning, and these VLMs, you can just do it end-to-end and not have this kind of two-part thing. What is a VLM that has 10x the amount of context and is also 10x the size? What does that world look like? Because I think that world is actually, right? Imagine a VLM that it's all the same. It's the same foundation model VLM. And then if you want a version of it that reads labels, you just have in-context example of like, here's a nutrition label, here's the output, here's a nutrition label, here's the output, here's a nutrition label, here's the output. And the VLM would consume all of that just to answer one question. And that sounds completely insane, right? Because you're like, Hugo, how are you going to have 100 images inside the context just to provide a single inference? What? No, of course we're going to have different VLMs that are fine-tuned for different tasks. And my answer to that would be like, actually, that's not where we ended up, right? Because if you ask someone in 6 years ago, are we going to have one language model that does everything? They'd be like, fuck no. You're going to have a language model for each specific task that's each tuned on each of those specific things. And that's not at all what we got, right? We ended up with language models that you prompt it or use some kind of in-context learning, and then it puts it in a specific mode, which is task specific. And maybe that's the same place we're gonna end up with VLMs, where we're just gonna have one VLM that is super generic, and you provide your little in-context learning data set or your fine-tuning data set directly in the context whenever you actually want to do your inference. Beyond. I'd like to see a breakthrough in conversational tuning where we can correct it in real time and tune it over time through everyday interactions and not have to edit the model through jobs. Yeah, it's basically what I'm describing, right? Where you are ultimately determining the behavior of your model entirely by choosing what to put and what not to put in the context, as opposed to having a model that was fine-tuned on this task, and a model that was fine-tuned on this task, and a model that was fine-tuned on this task, and then just choosing between these different models, right? Okay, is there something here? Preliminary experiments suggested that the model performance does not improve with information about previous states, likely due to limitations of existing models in processing long context. This is in contrast to this paper where they actually did improve, right? So in this paper, they add the successful demonstrations and unsuccessful demonstrations, and it improves, but in this one they don't. So a little bit of a conflicting things there. Comparison of evaluator accuracies against Oracle evaluator or human judge. I thought this was kind of weird, but Captioner plus GPT-4 versus GPT-4v. So this is the dichotomy, or the two different ways that I'm talking about, where you're just using the VLM directly versus using a VLM to caption and then using the LLM to reason. But kind of weird here, but look at this. Captioner plus Mixtral, 92 on Android, but then Web Arena, 74. So like, what is it about Mixtral that is very good at answering questions about Android? Right? Like, what is going on there? That's some weird stuff. Okay. Let's go down here. 2 approaches to implement a model: an end-to-end approach using a pre-trained vision language model, and a modular caption then reason approach using a VLM and a pre-trained language model together. These methods offer trade-offs between performance, cost, and modularity. Yeah, I think that my prediction is that we're just going to do this one. We're going to make an even more general, bigger foundation VLM that basically does any task based on what examples you put in the context. And the context is going to be so big that you're going to be able to put entire fine-tuning data sets on here. Saskia with a good point there. 50% of the human cortex is devoted to visual processing when only 5% for language. Yeah, a lot of the human cortex is also like movement and motor neurons. So like that might just be like a quirk of the fact that you need a lot of neurons to map to all the different muscle cells and things like that, and like sensory cells. So because we know that you can have a model that has a lot less parameters but is very powerful, right? Like you just got to look at the sparsity research where they take a model and like prune 90% of the neurons, and it's still basically able to do the same thing, right? So even though certain parts of our brain might be small from the total number of neurons, the like intelligence of that is not comparable, right? $8K 2030, $16K 2050. Somebody had a good response to Jan LeCun. Jan LeCun loves to, like, he memorized all the numbers around the visual cortex. So like every time you hear an interview with him, he like brings up his like little factoid about the human brain. Like there's a certain amount of information that goes through the eyes, and then a certain amount of information. He's like, but then someone was like, okay, but the blind people are still pretty smart. And I thought that was a great rebuttal, right? Where it's like, Jan LeCun is trying to use the numbers around kind of the throughput of the visual cortex as a argument for saying that our current paradigms are missing a factor of 10 here and there, right? There's still 10x's missing to do. But the rebuttal of like, hey, blind people can still learn and be very smart despite not having any visual information. So what does that mean, right? It's not just sheer amount of data equals intelligence. Pratyush, have you noticed that all VLMs are smaller than LLMs? Yeah, that's kind of what I was saying, where generally the vision language models, which are just a vision encoder with a language model glued on top, right? The language model that they use is usually quite small, but that's because just if you want to use a vision language model, the memory of the image and the image encoder, and then the fact that you have to fine-tune that whole thing, that's why a lot of the Lava models, for example, that are fine-tuned on smaller setups, they use a small language model. But there's no reason to do that. You don't have to do that, right? You could use a 70 billion parameter language model for a vision language model. And in fact, that's probably what Grok 1.5V did, right? They got good scores here, and I bet you part of that is because maybe Claude 3 Opus GPT-4V, the language model part of these VLMs is kind of small just because they were thinking about inference, right? They're like, hey, we don't want to have a huge inference cost. We can't have GPT-4V use a giant-ass language model, just have like a little language model, which means it's okay at captioning but not okay at kind of reasoning. But maybe Grok 1.5V, one of the easiest things that they could do is just make the language model part of the VLM very big. And we know that they're okay with that because if you look at the previous release, the language model Grok, it was huge. It was like 100 billion, or it was bigger than any of the other open source models, right? So we know that the Grok team is okay with just 10xing the model size. So I bet you they just 10x'd the size of the language model component of this vision language model in order to try to get the highest possible score they could on the benchmarks. Okay. Is there something else I wanted to talk about here? Web Arena. Oh yeah, this is another one. There's not much to talk about here, but Web Arena is another benchmark paper kind of similar to this one here, the OSWorld. OSWorld is about benchmarking like operating system things. So clicking, opening windows, moving files around. I think this is probably harder, and this one is just on websites only. But interestingly, they both kind of get around the same score. I think I mentioned that already, but 12% success on OSWorld for the current state of the art, and then 14% success on Web Arena for the current state of the art. So we still got some room to go. Let's see if there's anything interesting here that I highlighted. Search for museums in Pittsburgh. What is the action space here? Let's see. So we got a state space S. We got an action space. What's the action space? Here's the same exact reward functions. Also a partially observable Markov decision process. An action AT given partial observation. Action results in new state. Transition function is deterministic. This is the part that I'm saying is no bueno, because our universe is not locally real. You can't have deterministic transition functions. Although in this case, because it's a website on a computer, it is deterministic. But I want to see if this is actual natural language action space. Compound action space that emulates the keyboard. Okay, so no. Figure 4 lists all available actions. Action space of Web Arena. Click, hover, type, press, go to. So it might be language. So like the actual actor or the policy model actually outputs tokens because it's a language model, but they're limited to this particular API kind of thing. What about the state space? I think the state space is probably also text. Is this the state space? Eval implementation intent? No, it's probably what they call the DOM. I think this paper introduced it, but it's basically a summary of the visual information that comes from these accessibility and packages for disabled people. So it's like these text descriptions of like what is on the screen and like where the things are on the screen. An XML format, that's what it is. Those are pretty popular. GPT-4V. Let's actually look at the tables here. Nope. Comparing against other benchmarks. Where's the actual score? Give me the score. E-commerce, Reddit, GitLab. GitLab is the other GitHub. It's the one that all the weird kids use. Ah, here we go. Chain of thought. Hint. GPT-4 versus Text Bison. All right, I mean, they don't really... I wish they would have done more here. 14%. That's really kind of lame. You can't have a benchmark paper and not benchmark like a lot of things, right? Like the whole point is that you want to give me something like this. Like, look how much better. This is the other benchmark paper. This one has all of them. It has Cog Agent, Mistral, Gemini Pro, GPT-V, Claude 3 Opus. So props to that. This is quite lame in comparison. 8, 4. Overall, 5, 2. screenshot plus the alley tree, or the disabled human XML drastically improves here. That's actually kind of interesting. Look at that. The screenshot is more useful than the XML that describes the state. So what this means is that an XML description of what is currently on the screen is not as useful as a screenshot, which is crazy to think about because the screenshot is getting fed into an image encoder like a clip model or a dyno model and then turned into some latent representation of what's in that thing. So you would think that the encoded image is not going to be as good as an explicit XML file that's literally like, here's all the different little buttons and things on the screen, but somehow it is. You see that? 5 versus 2. 12. I guess this one is better. Okay, never mind. GPT-4v gets 5% versus GPT-4 gets 12%. Okay. Yeah, I don't actually know what I'm saying here. Screenshot plus the ally actually performs worse, 12%, than just GPT-4 on the ally tree. The original XML contains millions of tokens caused by countless elements, redundant attributes. We opt to filter out the non-essential elements. Okay. So it's not just the pure XML. They like filter it. Again, this idea that we keep seeing in pretty much all these papers where you're basically, the most important part of an agent is this filtering and intelligent RAG type variants that are basically choosing what to put into the LLM context, right? That's basically what's happening here, is that you're using some loop, some human designed system that uses other language models in there to determine how to put the text into the LLM that's going to actually do the thing. So we're prompt engineering. Tim Stewart saying he loves GitLab. The ally section looked like it was using Mixtral instead of Claude for some reason. Yeah, I don't know. I don't know why they didn't put Claude here. Right? That would have been kind of cool because I know there's still some contention that the GPT-4v and Claude 3 opus are kind of head to head. I think Claude 3 was ahead of GPT-4 when it came out, but the new turbo version of GPT-4 is above. So I actually canceled my Anthropic subscription already, guys. I know that might flame some of you people, but I had the Anthropic subscription when it first came out because I wanted to try it, and I used it. And then now that this turbo model came out, I just unsubscribed. No one using DSPy? Are you talking about a specific package here? I think they use... This is the real package that you want. They mention it somewhere here. Maybe here? Yeah, this one, PyAutoGUI. PyAutoGUI lets your Python scripts control the mouse and keyboard to automate interactions with other applications. It works on Windows, Mac OS, Linux, and runs on Python 2 and 3. So, look at this. PyAutoGUI, click, click, move to, current mouse position, screen width. So if any of you guys want to fuck around with agents, this is definitely the package you want to be using. Look at that. You can draw a perfect little square in Microsoft Paint. I don't know. I also think that, like, much like anything in kind of AI world, building things in little projects is fun, but you're not necessarily going to be doing anything, right? Where, like, all the big companies are working on agents, and the agents are going to be integrated into the products that they already offer, versus any agent that you yourself build directly in Python it's as soon as they release their own agents, then whatever you built is kind of dead. So I don't know. It's a little bit unfortunate that like the way that this is all evolving right now, the best action for you as an agent to take in the world as a little human is just to sit there and wait. But that also makes it very easy because you don't have to do anything. You can just sit there in your house and just wait, and then eventually it's all going to get solved. Sierpinski curve. What is that? Sierpinski curve. A Sierpinski curve is a recursively defined sequence of continuous closed plane fractal curves discovered by Wacław Sierpinski. Look at this OG. Which in the limit completely fill the unit square. Okay, so it's basically just fractals inside a unit square. Here's a function coded in Java. Gross. Oh shit, what? Three-dimensional Sierpinski curve? That's pretty cool. DSPy is a framework like Llama Index, but more DSPy. Let's look this up. Give that a star. Programming, not prompting, foundation models. Okay, so what's the distinction here? Algorithmically optimizing LM prompts and weights, especially when LMs are used one or more times within a pipeline. Okay, so prompt engineering and then fine-tuning. Okay, so this is the break the problem down into steps, prompt your LLM well until each step works well in isolation, tweak the steps to work well together, and then generate synthetic examples to tune each step, and then use these examples to fine-tune smaller LLMs to cut costs. Or you can just get rid of the fine-tuning and then just have a little set of prompts for every single thing. Separates the flow of your program. DSPy can routinely teach powerful models. Well, it can't because you can't fine-tune into 3P. You can only fine-tune with smaller open source models. Chain of thought, React. Okay, so it's just kind of like a... For the alphabetically script. Introduces example, teaches a local T5 to do exceptionally well on Hotpot QA. Tackles extracting information from long articles. Combines in context with retrieval. See, this is what I'm talking about here, right? So this advanced information extraction here, right? Oh. Like you have to now have the context or the concept of a chunker, right? Where it, because language models had this context limit, someone had to basically design this system that chunks it into these chunks and then goes through this whole process, right? But then as soon as Gemini 1.5 came out and you had 10 times the context length, you don't have to worry about this shit ever again, right? Dividing the paper into chunks. It's also a spelling mistake here. This is divides. It should be divides. So that's kind of what I'm saying. It's like a lot of these tricks that we have right now and a lot of these kind of over-engineered agent loops, once you 10x the context length, once you 10x different parts of the system, you might not even need those things anymore. But you have to send, yeah, like you are correct, right? Like what I am saying is incorrect in the current paradigm, but that's not how you predict the future, right? Predicting the future is usually about realizing that something that is incorrect in the current paradigm is going to be correct in the future, right? And this is why like there's sayings such as like science advances one funeral at a time. The reason that saying exists is because the people who are dying have a lot of experience, and experience means that they tried to do something with the technology at the time and it didn't work, so that whenever they think about how to do things in the future, they're kind of within the framework of their own time. And younger researchers who don't have the experience, don't have that intuition, they do what is technically a mistake from the perspective of an older researcher, but it's no longer a mistake because the technology has improved. So right now, putting your entire fine-tuning data set into the context of an LLM and doing everything in context learning seems like a complete waste of inference, and it's just not going to work. But maybe that's what I'm saying, is that if you just wait for the context to 10x and we get better and better at inference, we figure out how to quantize better, we do some of that mixture of depth, right? Mixture of experts, all these different tricks to reduce the inference budget, then maybe what initially sounds like a completely stupid idea, which is like putting your entire browsing history into the context of the model that you're using every single time that you're using that model, might actually turn out to be the best idea. We just have to kind of wait. Yeah. Partially gets solved with a KV cache, so it should not be that inefficient. Infinite KV cache. Yeah, bitter lesson. All right, guys, let me sip this water, do a little bit of a summary, and then we'll go from there. All right. So in today's stream, we spent a little bit of time hanging out. Appreciated all the questions, all the back and forth that you guys had. You know, I love interacting with chat, you know, because you guys collectively are much smarter than me. That's kind of like the cool thing. And I didn't realize this until I started streaming, but having like a little hive mind that I can talk to is actually incredibly cool, right? Because it's like kind of from the collective intelligence kind of intuition, right? A collection of humans is way more intelligent than a single human. So when I'm sitting here kind of reading these papers and I have this like hive mind of people that is like feeding me ideas and like, oh, technically this and this and this and this and this, it's like, that's pretty badass. You know, it's like a ChatGPT before there was ChatGPT. Okay. Let's do the summary though. So we looked at some agent papers. The TLDR is that the agents are just not quite there yet. So we started off the stream by bringing up this drama that apparently some of the more hyped agent demos, such as Devon, are a little bit faked, you know, where they're basically like kind of like glossing over the fact that it takes forever and that the tasks are kind of cherry picked, and it really doesn't work that well. And based on the papers that we read, that seems to be the truth. So there's two different benchmark papers that we looked at. We had one benchmark paper that is for like web crawling, or like kind of like clicking and doing stuff on the web. And the current state of the art is about 14%. And then we also saw this paper, which is more operating system tasks, like moving windows around, like opening up applications, doing things on those applications, also very poor. So 12% success for the state of the art on that. So we're still not getting very good success with these agents. Right now, what agent loops basically are is, I guess I can start with that, but I can start with this. So most of these agent loops are specific to a task. So we have these task-specific agent loops, which are designed by humans. And these task-specific agent loops are basically all designed on reinforcement learning ideas, right? So this core concept behind reinforcement learning of the Markov decision process, specifically a variant of that called the partially observable Markov decision process. This idea of having action spaces, state spaces, observation spaces, the idea of having functions such as the reward function, the transition function, the value function, the policy is also a kind of function, right? And approximating all of those with neural nets. And the more modern version of reinforcement learning, which is what we're seeing in these agent papers, is taking all the same ideas from classic reinforcement learning, but now replacing all the neural nets with language models such that your state space can be pure text, your observation space can be pure text, right? And that, I think, is a good thing. I think it adds like a new, fresh coat of paint on top of some of these RL ideas, which are a little bit stale, but we're seeing them kind of work better now that you have this fuzzy natural language state space, and action space, and observation space. What else? We saw how these agent loops are hard-coded. So we saw two different types of agent loops. We saw one that was used for research, so summarizing papers and generating research ideas. And we also saw an agent loop that was specialized for web agents. Both of these are preprints. And they kind of work, but they're definitely kind of hard-coded. There's ideas in here that I think they could both benefit from. So you could imagine that a superset of both of these agent loops would probably work better for both tasks. And maybe that's where it's all going, right? Maybe eventually we have kind of an agent loop to end all agent loops, and it's just like this giant superset of all possible types of RAG. But it feels to me like we're probably going to figure out something that's less explicit, less kind of heuristic, and more fuzzy and generic. But for now, pretty much what all these agent loops are doing is they're doing fancy RAG, right? This retrieval augmented generation, this idea of like, I have some cold memory storage and I'm selectively picking the right things from there, maybe spending some time to do planning in natural language space where I'm basically taking out certain trajectories, putting them in here, adding more trajectories into here, then picking them out here, right? All of these are variants of that type of idea where you're not really fine-tuning models. What you're doing is you're doing everything in context. So you're basically picking and choosing what you're putting into the context of the model such that the model is specific to some task, right? So it's all just fancy RAG and in-context learning. And then we spend a bunch of time kind of hypothesizing and theorizing about where this all goes, right? Where if we're getting better and better context lengths, we're getting 10 times the amount of context, 10 times the amount of context on top of that, right? Then maybe maybe fine-tuning starts to disappear, and maybe everything becomes in-context learning and RAG. Maybe every time you go into GPT-4 and type something, it's literally putting your entire internet history into the system prompt and you don't even realize it. And even though that seems completely crazy, maybe that's easier than maintaining a bunch of different LLMs that are fine-tuned for each individual user and then pulling them up. And then anytime you have to update the model, you have to basically retrain everyone's custom little fine-tuned LLM, right? It feels a lot easier to just have one LLM and then just change what's in the context. A lot of these papers had this idea of these kind of value functions, these reward functions, basically some kind of queue function, if you want to think of, or if you want to use reinforcement learning terminology, something that is consuming states and actions and then telling you the value or like how good that particular state action or that trajectory is, right? And we kind of maybe predicted what Q star is, which is A star with some value function Q, or with some Q function that is parameterized, or that is a language model, right? So there's some language model, which is a type of deep learning model, which is a type of function approximator approximating this optimal Q, and you just collect enough trajectories that you get a Q that kind of makes sense. And then I think I also want to mention this. So another thing that we briefly talked about was how right now a lot, especially if the actions or if the state space is images, and in a lot of these benchmarks, right, you're feeding an image of the screen. The way that it currently works is people are using vision language models to caption the screen, so turn it into a bunch of text, and then feeding the text into a language model that is doing the actual reasoning, versus doing the whole thing end to end with a vision language model. I think is probably ultimately the more powerful way to do it, because then you only need one giant foundation VLM that you can do everything in context. And that just seems like the cleanest possible solution to me. But it's also going to require a couple 10x's when it comes to inference, a couple 10x's when it comes to just like the amount of memory you need to store this, right? Like imagine making a VLM that can consume like 2-hour videos and not be slow. But IDK, that's pretty much it, guys. That's all I got. The universe is not locally real. That's why Markov decision process is a bunch of bullshit. But maybe we can all be happy like this little guy here. All right, that's all I got, guys. Thanks, Saskia. Thanks, Tarun, Beyond, Ed, Khalil, Timothy, Christopher. Who else? Josh. Scrolling. Pratyush, Majetti, Cheb Khaled, Emily, Christopher again, Oma Viva, Pratyush, Arya, Jack Z, Sarah, Khalil, Tarun. Thanks, everybody. Thanks for the chat. Keeping it cool. This is the only stream I have this weekend. I have some other stuff that came up, so I'm only going to be able to do one. I'm sorry, guys, but I got stuff to do. Hope that was kind of interesting. If not, have a great weekend. See you guys later, and